Did it work?
Yep, perfect.
Is it the right screen?
Yes.
Okay, so I would really like to thank you guys for inviting me. I love traveling to Houston and Rice, and I would wish I were there, but I'll do the best I can remotely. I'd like to, so what I'm going to talk about is the Pyrrhus phase, charge density wave material phase that we observed in this barium nickel arsenide material. I need to acknowledge Sang-Jin Lee, who is the grad student. This is his PhD thesis. And in particular, JP Paglione for not giving up and working on this material for 10 years and introducing it to me. I apologize for not taking an interest earlier. Okay, so I guess this series is about pnictide iron arsenide superconductors. So you've probably seen these pictures a lot. So this is the structure. The high temperature phase is I4MM, and there's a superconducting dome and antiferromagnetism with the tetragonal to orthorhombic phase transition. So you've seen all that a lot of times, I assume, by now. What I'm going to talk about is this nickel analog, barium nickel to arsenic 2 that JP just showed you, but I'm going to focus more on the structure. I have some data about the possible tetragonal phase versus triclinic phase near the phase boundary that I can share if as a supplement slide. At any rate, this is the structure. It's identical to the iron arsenide 122 materials. The lattice parameters are a little different. C is a bit smaller and A and B are a bit larger. But otherwise, it has the same high temperature structure. It's I4MM body-centered tetragonal. But when you cool, it doesn't go orthorhombic. It goes triclinic at a triclinic transition of 136 Kelvin, which is slightly first order. And the triclinic space group is P1 bar. So that's the lowest symmetry you can have that still has body-centered symmetry to it. So the only lower symmetry is P1 is minus bar. So, and as you heard, this material is superconducting with a TC of 0.7 Kelvin. So it's an interesting analog to the iron arsenides. So if you dope it with cobalt, then the phase diagram looks a lot like iron arsenides. So this triclinic phase acts kind of like the orthorhombic phase in the iron arsenide materials. And then there's a superconducting dome-like thing here. The triclinic phase is split. There's a little bit of first order character and some hysteresis. And as you dope with cobalt, I guess I should call it substitution, but I think you understand what I mean. TC goes up to about 2.3 Kelvin. So JC apologized for the superconductivity being low temperature, but I'm going to show you the charge density wave set in at quite high temperature. So this material is actually sits somewhere halfway between the pnictide superconductors and the transition metal dichalcogenides, things like tantalum disulfide and so on. Okay, so the structure is similar, but TC is much lower than the iron arsenides. And very important, nobody has found magnetic order in this material yet. There's been quite a few neutron studies and nobody has found antiferromagnetism. So there's been a question for a while, which is what exactly is this competing phase here? So the latest work from JP's group was this uniaxial strain response, which you just heard all about. And what he showed is near this triclinic transition, there's a region where the pneumatic susceptibility is extremely large. Overall, the phase diagram looks a lot like the cobalt phase diagram as well. There's a first order quantum phase transition. So it's a quantum phase transition, but not a quantum critical point at 0.7, across which the triclinic phase disappears. And all along this boundary, there is a big pneumatic response. And then down here, that enhances superconductivity by a factor of 6, which you just heard about in the previous talk. I want to point out a couple of things. The first is in this region here, the pneumatic response is hysteretic. Out here, there's still a big response, but it's reversible. So it looks like there's some kind of static order or domains forming in this region that become dynamic out here. And for me, when I look at this material the first time, I asked several questions. One is, what is going on with this strange superconducting state here? So so JP just told you, in this region, the thermodynamic and transport signatures of superconductivity are split. So the black points are where the resistive transition is, and the blue is the specific heat. So just on the left side in the triclinic phase, these these things are split. But if you get rid of the triclinic distortion, everything sort of becomes normal. So the question is, what is it about this triclinic phase that is making the superconductivity behave so odd? And also just in general, what is this competing object sitting here? If it's not antiferromagnetism, then what is it? So in my group, we do a lot of experiments using advanced spectroscopy, scattering at synchrotron facilities and stuff. Everything I show you in this talk was done on a lab source. So this is an instrument we built in our lab. I actually originally built this just to train graduate students how to do scattering before we took them to the synchrotron. But everything we found was measured on this lab source. So it's just a molybdenum K-alpha microspot X-ray source with a liquid helium cryostat with a base temperature of 4 Kelvin with some beryllium domes and so on. And then we have a large area image plate detector. And so this thing lets you do full reciprocal space mapping. And before I get into the details, I want to point out a subtlety. So in scattering, one always specifies momenta in terms of Miller indices, HKL. There are two different sets of Miller indices depending upon whether you're in the triclinic phase at high temperature, the tetragonal phase at high temperature, or the triclinic phase at low temperature. So it's crucial to index everything in the unit cell in the phase where it exists. So I'm going to put a little subscript next to every HKL that says which crystal system we're indexing. So if you see a tetragonal there, that means the HK and L correspond to tetragonal, the tetragonal unit cell, and triclinic is the triclinic unit cell. And just let me back up a second. So this is how we've defined them. So this, in the high temperature phase, we use this orthorhombic unit cell. It's the normal one for the pnictides. The triclinic state, we use the reduced cell, which is this one. The only difference between these is, well, the main difference is, the only similarity between these two cells is that this barium atom is still crystallographically equivalent to this barium atom. But other than that, all the atoms become distinguishable in the low temperature state. Okay, anyway, so that's just the way we've defined it. Okay, so here's the main result. If you cool this stuff off, you see a superstructure. So these are some maps of momentum space. This is in the tetragonal phase. So if you look at, this is at 142 Kelvin. So this is just above the triclinic transition, which I think is at 136, if I remember correctly. I wrote that down somewhere. Yes, 136 Kelvin. So what you can see is that there are some superstructure peaks that form. And this implies that there is a superlattice in the crystal structure. It's not appropriate to call such a thing a charge density wave because there are a lot of different ways you can get a superstructure. But it's important to point out that you can see whatever these reflections are in multiple Brouillon zones. So the thing that makes you know this is a real superstructure is that you can see these things all kinds of places in momentum space, which distinguishes it from little spots due to scattering from the beryllium domes or the sample holder and so on. So whatever this thing is, it has a periodicity of 0.28, so it's incommensurate. That's the wave vector in tetragonal units. And it shows up quite a bit higher than the triclinic transition. So you can start to see these things at 150 Kelvin. And then they get stronger and stronger as you cool. When you cool into the low temperature state, so this is also a cut in, but now in triclinic units, another charge density wave forms. And this thing has Q of 1/300 in triclinic units. Okay, and this again is a coherent superstructure. You see it in many different Brouillon zones. So it's a real supermodulation in the crystal. And the amplitude, we've done some estimates, and it's something like somewhere between a few hundredths to a few tenths of an angstrom. So this is extremely large. The amplitude is actually similar to well-known structural charge density waves in things like tantalum diselenide, tantalum disulfide. The transition metal dichalcogenides are of the same order. So whatever this instability is, the electron-phonon interaction is playing a critical role. Okay. But it is not a simple nesting. I have a backup slide on the ARPES. So you don't get Brouillon zone folding and gaps opening like you would expect if it were a simple chiral state. So it's not a textbook thing, but the lattice is involved in some way. Okay, so
Peter,
yeah,
you mind being interrupted?
Please.
So this notation 0.2800 or extra both and 1/300.
Yeah.
Is that in the nickel-nickel bond direction, or is it some other direction?
It is in, I actually have a picture of the Brougham zone.
Oh, thank you. Yeah.
It is an angle between the nickel. It's triclinic, so everything is at an angle. Let's see, but it's only triclinic in one direction. So you're asking, is it in? I think it's roughly 45 degrees between the nickel-nickel bonds.
Okay, so it's rotated away from what would be the wave vectors, the patterns of the magnetism in the ion systems.
Yes, it's in the, I think if into tetragonal units, you'd call this the pi-pi direction. But I think
Okay, thank you.
magnetism is also pi-pi. So, well, that's right. It's stripe antiferromagnetism.
Okay,
Yeah.
thanks.
So this is 45 degrees. Yes, okay. So these two, this is very important. These two Qs look very similar. 0.28 is not far from 1/3. But this is triclinic units and this is tetragonal. So these are in very different locations in momentum space. So this is what the Brougham zones look like. The black is the Brougham zone in the tetragonal cell. The red is the triclinic cell, the way we defined it. And you can see there are two planes here. There's a gray plane, that's the HK plane in the tetragonal cell. The red is the HK plane in the triclinic cell. And so this incommensurate CDW at 0.28 is sitting at these 2 points in this gray plane. So those are so they're in this gray plane here. If you, in the triclinic planes, this thing we call CCDW2 is sitting at this point. So even though the Miller indices are very similar, these two CDWs are about 20 degrees apart. So they're completely different charge density waves. I can talk more about that if you like. So don't let the indices fool you. They're really different. It's not a commensurate, incommensurate transition. They're really completely different phenomena. Okay, so not all structural modulations are charge density waves. For example, BISCO, if you know your high TC, has a supermodulation. It has nothing to do with CDWs. It just has to do with the fact that the bismuth oxide layers and the copper oxide layers have different periodicity. So when you put them together in a crystal, there's internal strain and it relieves itself by creating a buckling. So that's called an adaptive misfit effect. So if you want to prove this is a charge density wave, you need to do something else. The thing that really convinced me is that it exhibits what's called a lock-in transition. If you look at the 1/3 state at a temperature a little bit below the triclinic transition, so 129 Kelvin, you can see the wave vector actually shifts with temperature. So if I look at 136 K, this thing is sitting at around 0.31 in the H direction, but as I cool, it shifts continuously. And then at a certain temperature, TL, which is 129 Kelvin, it pins on the lattice to a wave vector that's exactly 1/3. So it's 0.333. So this kind of effect is sort of a smoking gun signature of a charge density wave. It's also takes place in things like tantalum disulfide. You know, in tantalum disulfide at high temperature, if you know your dichalcogenized, there's an incommensurate CDW. You cool, there's a nearly commensurate CDW. That's kind of like this. And then that thing locks into a commensurate wave vector below the low temperature transition. This thing exhibits almost a very similar phenomenology. So it's kind of like, so the material is sort of halfway between a pnictide superconductor and a dichalcogenide in the sense that in the way the charge density waves behave.
Peter, may I ask to clarify? This is Andrei Nevedomsky. When you index the peaks, are you taking the lattice wave vectors at whatever the lowest temperature measured? I mean, are you taking into account the thermal expansion?
Yes, we take into account the thermal expansion. So the lattice parameters are temperature dependent, not hugely, but a little bit, and every peak is indexed with respect to the lattice at that temperature.
So the drift that you show here has nothing to do with the lattice slightly expanding.
No,
Okay.
and that was crucial to prove that this is true. You have to normalize that effect out. It turns out if you don't correct for that, you can still see this because it's more than an order of magnitude bigger shift than what the lattice parameters do. So even if we didn't do that correction, you could still trust the result, but we did that correction.
Thank you.
Let's see. Yeah, so what this really tells you is that at high temperature, there's something determining what the Q vector is, something related to the Fermi surface or electronic structure in some way, and that's competing with the tendency of the CDW to pin on the lattice. So those two effects compete with each other. And then at high temperature, there's one Q, and then it shifts, and at low temperature, there's a pinning effect. Okay, and I don't know how I'm doing on time, but I think I tried to make a 30-minute talk like JP. Okay, so we spent a lot of time trying to understand whether these CDWs break rotational symmetry. This was especially important when Paglione group started to see nematic phenomena. So there's a question, are these CDWs C4, they have rotational symmetry, or is it C2, meaning it's some kind of unidirectional order? So if you look at the CDW1 phase, that's the thing with a wave vector of 1/3, it is clearly unidirectional. So if you do a wide mapping of momentum space, you can see all the reflections lie in the same direction. You never see the companion reflections rotated 90 degrees. So this is a 1Q unidirectional state. Okay, let's see. But if it turns out that the incommensurate CDW is bidirectional, so this thing lives in the tetragonal phase above the tetragonal phase transition, and it is actually C4. Our original paper on this, which was published in 2019, was wrong. I think I can be a grown-up and admit when I'm wrong. So I was wrong about this. And the reason I was wrong is actually quite subtle. If you look in a given Brouillon zone, what you can see is that there are pairs of reflections, and they're unidirectional. You'll only see a pair along the H direction or the K direction. So in some zones, you see them along H. Some zones, you see them along K. When we originally did the study, we only looked at a few Brouillon zones, and they were all oriented along one direction. And what we concluded was it's a unidirectional CDW because you only see reflections in a certain way. But if you do a wider mapping of momentum space, which we went back and did, you can show that the actual pattern of reflections looks like this. So if you look in any given Brouillon zone, there are 2 reflections, but the overall pattern has 4-fold symmetry. So even though the low temperature state is C2, it's a unidirectional state, in the high temperature state, in the incommensurate phase, it's actually C4. It's very important because the symmetry of this thing is different in the high temperature tetragonal phase than the low temperature phase. It kind of makes sense because it means that the system really is tetragonal even when the CDW is present. So where are the other pairs of reflections? They're actually extinguished by symmetry. So this happens in crystals like, in silicon, there's a 1-1-1 reflection and a 3-3-3 reflection, but there's no 2-2-2. It's forbidden by symmetry because there are 2 silicon atoms in a unit cell and they're identical. So there's some kind of internal symmetry in this modulation that extinguishes some of the reflections. But anyway, the overall thing is C4. So that was incorrectly reported in our earlier paper, but it's corrected in the new one that was just posted. Okay, so if you dope with cobalt, this is the phase diagram that you get. So up here at very light doping, there's this incommensurate phase. And then as you dope, everything gets suppressed. The incommensurate phase goes away and all the TCs of everything else disappears. This line is the incommensurate to commensurate transition. We call that TL, that's the lock-in line, and that goes to 0 somewhere in the middle of this dome. Interestingly, there's an extended region of coexistence where you have both triclinic and tetragonal phases in part of the phase diagram. Down here at low doping, low substitution, it's purely triclinic, but at higher levels of cobalt content, the 2 phases coexist. So it looks like there could be some kind of disorder or so on, but the CDW order is very long ranged. Okay, so what does this have to do with nematicity? So JP spent a few minutes telling us about barium-strontium nickel arsenide, which is definitely not doping because barium, this is like pressure. Strontium is above barium. So the question is, what happens to these charge density waves in this system? And here's the result. So at low values of X, everything is the same. So there's an incommensurate phase. At X equals 0, it's the same material. At very small values of X, there's an incommensurate phase, there's a commensurate phase. The commensurate phase has wave vector 1/3. But as you continue to dope, something very surprising happens. At x greater than about a quarter, a third charge density wave appears. So it has a wave vector of 1/2. So it's 1/2, 0, 0 in triclinic units. So if you take the material with a composition of 0.47 and just measure it as a function of temperature, it does something, it shows 3 different charge density waves as a function of temperature. I've studied charge density waves for 25 years. I've never seen this. So as you cool, this incommensurate phase forms, and then that dies quickly, and this period 3 commensurate phase forms, and then that dies, and then a third CDW with period 2 appears. And these 3 things seem to compete with one another. This is the advantage of being an experimentalist, is I don't have to explain this. I can simply report that it's true. The period 2 phase, if you do a wide momentum mapping, and I can show you that if you like, is also unidirectional. And so it's at the high temperature state where the system is tetragonal. The CDW is also 4-fold symmetric, but in the triclinic phase, everything becomes unidirectional. So you can have a conversation. Is it unidirectional because the system is triclinic, or is it triclinic because it formed a charge density wave that wanted to be unidirectional? And I don't know the answer to that question, but that's an interesting thing to investigate. Okay, so just to be clear, when I say they're all different CDWs, they really are in completely different locations in momentum space. So before I showed you, this is the incommensurate CDW in the tetragonal phase. This was the CDW1 in the triclinic phase. The CDW2 sits out here at the zone boundary. So they're really quite far apart. And they almost look like they're different kinds of instabilities that are just competing with one another. So the final phase diagram looks more or less like this. And we tried to put it together with the pneumatic response reported by Paglione et al. And what you can see is at low doping, so this is the incommensurate phase here. This is the commensurate phase with period 3. And as you dope, this period 3 CDW disappears and you get this period 2 state forming instead. And then the incommensurate phase at sufficiently high doping disappears. So I need to point out 2 things. The first thing is that everywhere you see the incommensurate CDW, the strain response is hysteretic. So if you remember when JP was showing you the pneumatic response, there was a region where he had these hysteresis loops. But then if you dope far enough, they become reversible. There's still a big response there, but everything becomes reversible. The region where it's hysteretic is where this incommensurate CDW exists. And the region where the incommensurate CDW is gone, everything becomes reversible. So it looks like there are sort of pneumatic fluctuations in the system, and when the incommensurate phase forms, it pins them, and they become static domains, which you can train like ferromagnetism in iron. So that raises some interesting questions, which is how does a thing that is 4-fold symmetric pin an object with a pneumatic order parameter? Because they have different, the order parameters have different symmetry. So I don't know how you could couple 2 such things, but that seems to be what happens. The other thing is it provides a lot of insight into what this strange superconducting state was down in this region about 0.5 to 0.7. On the left side of this first order line, there was this odd superconducting phase where the thermodynamic and transport properties, the signatures of superconductivity are split. The resistive transition sets in and the thermodynamic transition is at lower temperature. That effect is entirely existent within this period 2 CDW phase. So I went and I talked to Eduardo Fradkin, and he said that makes perfect sense because a charge density wave with period 2, the order parameter is always real. Because if it's period 2, then the phase of the order parameter is always pi or minus pi. There's nothing else it can, no other value can take on. Or in other words, it's always just 1 or minus 1. So if the order parameter is real, anytime you form a domain wall, the order parameter has to go to, the gap, the order parameter of the CDW has to go to 0. So if I have a period 2 CDW coexisting with a superconductor that it's competing with, then it should produce a filamentary state where you get superconductivity localized at domain walls in the charge order. And that's a possible explanation for this. So he has a theory of that that's in this. I can't explain all the algebra, but it's in an extensive supplement in this paper we just put on the archive. Okay, so I'm done. I just want to point out, we were inspired by JP, so we made a copy of his strain cell, and we're now doing measurements of this material under uniaxial strain. And you can already see there's a big response. So if you measure these X-oriented and Y-oriented CDW reflections, and you put the system under a strain of just a few times 10 to the -3, then you can actually show that the two wave vectors, the incommensurate phase, respond completely differently. So it looks like the incommensurate phase really feels uniaxial strain a lot. If you look in the commensurate phase, or even the crystal structure itself, it essentially doesn't care about strain at all. So there's some connection between the strain response of the system and the incommensurate state. Okay, so that's the end. In summary, these materials are really exciting. I'm glad JP didn't give up, and I apologize for not taking an interest 10 years ago when he was first doing this. They do a lot of things like the iron arsenides is similar. There's a structure, there's pneumatic phenomena, and there's some competing instability like antiferromagnetism. The only difference is it's a charge density wave. And the phenomenology, at least in the parent compound, is very similar to tantalum disulfide. So this is kind of like the pinictide superconductors where you put some dichalcogenide physics in there instead. It is definitely a lattice-driven CDW, but it's not a simple chiral state in the sense that the nesting vectors and such don't make sense. And whatever the incommensurate phase is, it seems to pin the pneumatic fluctuations leading to a hysteresis state. And this period 2 CDW is somehow responsible for the anomalous superconducting state they reported, perhaps through a domain wall mechanism Eduardo has proposed. That's the end. Thanks.
Thank you very much, Peter, for this really interesting talk. I'm gonna ask my questions because I feel like I won't get to. Wait, can I ask? You mentioned that you have evidence from ARPAS that shows it's not a nesting driven.
Yeah, Dong Lai Feng's group in Fudan did a lot of ARPAS.
I see, it's from that paper. And
And
the other question,
yeah.
yeah, sorry.
oh, well, I'll just tell you, the only thing that happens is at low temperature, you don't see it. There's electron pockets, hole pockets. It's similar to the iron arsenides, but with the Fermi energy in a different spot in the band.
Mhm.
What happens at low temperatures is you get these little alpha pockets forming. You don't see a clear folding of the zone or a gap forming. You just get these extra pockets. The Q, the vector connecting them, is the same as this triclinic Q vector. Why is that? I don't know, but yeah, the first thing you ask when you see a CDW is what's the Fermi surface doing? This is what it does.
Okay. Sorry, can I just I'll ask another question before I let.
Yeah.
So since Christoph mentioned that there is a symmetry broken state in the regime where there was an incommensurate charge density wave, is it possible to explain the diffraction pattern by thinking there's domain mixing, and then in each domain there's unidirectional CW to explain the?
I can only tell you we don't see any symmetry breaking in that phase. There may be, we're not the only group working on this. There's a lot of X-ray data from groups in Karlsruhe and other places that have worked on this. I'll show you what we see. So if you just take this point, any of the materials and you cool, this is what the transition looks like. So in the high temperature state, there's nice sharp Bragg peaks. When you cool, they split into triclinic domains. And these are twin domains, and you can measure their periodicity and everything. And all the data I showed you indexed is actually taking one of these satellite reflections and indexing a part of the crystal and calling that so you pick one twin and index with respect to that. There isn't a phase in between that we could call orthorhombic, but right at the phase transition, this thing has some funny shapes. Maybe you could try to index that as something else. So this is what we get.
Okay, thank you. Maybe then I'll let Christoph ask the first question.
I was sort of going in the same direction. Actually, from the diffraction data in Karlsruhe, we also don't have evidence for the orthorhombic phase, but we do have evidence from the high-resolution thermal expansion, which is much more sensitive than the X-ray diffraction.
Yeah.
So I think there's a very clear evidence for orthorhombic phase, and this, I think, naturally would explain your hysteresis in this phase. You have domains.
Yeah, okay, could be. So that would be, if that's a very tiny effect, it might be living in this peak here.
Yeah.
And then it could be, yeah, I'd be really interested to see that data.
the evidence is, well, it's on the archive. Huh?
On the archive.
I'm sure I sent it to you, I think, no? Okay. So I think the evidence for the orthorhombic phase is quite clear. Huh? There's a real phase transition, which breaks the symmetry there.
Yeah, I mean, it would make sense. It's really hard to go from tetragonal to triclinic P1 bar without going through any intermediate symmetries.
Yeah, that's what we explained in the paper.
Yeah, that would make sense.
Yeah. Okay.
Okay, Pengcheng, what's next?
So I have two questions. I guess the first question is that, I mean, what happens in the L direction, C direction? I mean, all these things that you're talking about is in the, I guess, nickel plane, right? Nickel.
No, they're at an angle.
Oh, they're at an angle. Okay, so
Yeah.
are there periods along incompatibility along C-axis or?
Well, it depends on what you mean. It's triclinic, so you can't, the momentum space axes are not parallel to the real space axes in this material. So it depends on whether you mean real space or momentum space. But if you take, say, for example, this Q equals 1/3 state. All right, it is sitting at 20-degree angle with respect to the planes. But that is the HK plane in reciprocal space because it's a triclinic cell. So you have to be careful what you mean.
I see. So do you have a model? I mean, you know, the sort of what sort of a lattice motion to give rise to these peaks?
No.
It's tough, right? It's tough.
I
right?
don't. Yeah. Well, we started working on one. The key thing is this. You know, when you do crystallography, the most important reflections are the ones that are not there, right? The ones that really constrain the symmetry are the ones that vanish, right? And so to get them to vanish in exactly this pattern is a very strong constraint on what the real space picture of the CDW is. So we started playing with that and we haven't figured it out yet. It's a math problem.
Okay, thank you.
Yeah.
But is it possible to decompose this into two domains in which?
If theoretically, yes. So if I took all the horizontal ones and I called that a domain, and I rotated it 90 degrees, I would get all the vertical ones. So it's not inconceivable you could explain it with domains, but it starts to be harder to believe.
But this can potentially be seen by electron diffraction, right? I mean, by using, you know, electron, which have a much smaller spot, right? Then you can separate the domains, right? Or
yeah, that would be a really good idea to do that. Yep.
Okay. Thank you, Mel.
Yeah, beautiful talk. So I was wondering, Peter, actually maybe one comment and one question. The comment is that in the process of understanding some still evolving experiments in this heavily hodled ion arsenides, we actually thought about how to link, you know, any density wave fluctuations at some particular Qs. How would that connect with the type of nematicity? And the statement is that so long as the density wave fluctuations are away from the ion-ion bond direction, you have a chance of getting nematicity that's 45 degrees rotated away from, you know, the direction that's picked by in the ion, in the usual ion arsenide cases. Okay. So it seems to me that you have all these, you know, various kind of static CDW orders that would imply that there should be fluctuations on,
yes, I was going to
number of different Qs, and some of which could be linked with the nematic order that's in I guess in this strontium barium cases.
Yeah.
So that's a comment. The question to you is that if the link is with the magnetic order, then there's neutron data that tells us how much spectral weight is living there in the fluctuating part, a different Q, different omega.
Yeah.
For this kind of CDW type of, in this CDW channel, how much information can you get experimentally for the inelastic spectrum, and also like how to quantify the total spectral weight that's living in the fluctuating part?
I mean, we can, okay, I have several answers. The first answer is, I have a hunch, I can't prove it, but I believe this incommensurate phase is dynamic.
Mhm.
And I need a different plot, but one thing this doesn't show is that this blue line is about a factor of 50 smaller than the purple, and the purple is about a factor of 10 smaller than the green.
Yeah.
So what really is happening is as you cool toward the triclinic transition, there's some fluctuations that are building up at a wave vector of 0.28, like it wants to form that phase, and it's still dynamic and hasn't asserted itself, but before it can form, it gets preempted by another phase transition with a different order, and then this thing is really static.
Some very low frequency fluctuations, presumably.
Yes, I can't, well, this is an energy integrated measurement, but
I see. Okay.
I bet, yeah. So, okay, then, so the answer to the second question is, can you get dynamic information? Yes, absolutely. We haven't done it, but, and then the collective modes of this material would be analogous to the spin excitations in the pnictides. The difference here is, you know, now the collective excitations are acoustic phonons. And the question is, are the phase on and amplitude on modes consistent with any common understanding of CDWs? And that's something we need to do.
But how much? I mean, it's my ignorance about the dynamical measurement in the charge sector. So in the spin sector, one can say, oh, you know, I get the total spectral in the fluctuation to be say 5 Bohr magnetons square per ion or some such numbers.
Yeah.
In the charge sector,
It's same.
the way to calibrate.
Yeah, we did that. That you can get from an energy integrated measurement. That's where this, where did it go? This statement came from the analogous thing in the charge sector. So what you get is, instead of the local moment, you get the local displacement amplitude of the structural distortion.
I see.
So how do you relate this to a charge amplitude? That's another experiment. You have to use resonance techniques to do that. And you can quantify these things separately. So.
Okay, thank you.
Yeah.
And then Andre?
Peter, first, if you allow me to make a quick comment, and then I'll ask a question. So the comment is about, I haven't read Eduardo's paper, but just from what you told us, if indeed the superconductivity sort of sits on the domain walls, which are periodic in real space,
yeah,
that means that upon Fourier transformation, there should be a K structure to this gap. So let's say you're inside the triclinic phase, there's a well-defined uniaxial direction of this charge density wave. Well, then it wouldn't be delta, wouldn't be just a constant in K space. It would look like something like delta naught times cosine of Q times R, where Q is corresponding vector. So in other words, what I'm saying is that if true, then it would look like FFLO state, literally.
yes. Or PDW maybe.
Right, or except, yeah, or PDW if you wish. And so if so, then this goes back to the question I was asking Jean-Pierre, is whether or not it's possible to then try to tease that information out either from laser ARPAS or STM-QPI or some form of Q-dependent information.
Okay, let me just be clear. There's no evidence that the domain walls are ordered. So the CDW has a well-defined periodicity, but the information about the domain walls is embedded in the momentum space structure of that peak.
Oh, so then I beg your pardon. So you're saying domain wall, I shouldn't interpret this as a twice periodic, it's not 2A.
It is 2A, but we don't know what that's the period of the CDW. The period of the domain walls is something unknown.
Oh, so it's not that. Okay.
There is disorder, so there certainly have to be domain walls, but we don't know anything about the structure of those.
Okay, so the domain walls, then I misunderstood. So the domain walls is some macroscopic object, right? It's not related to 2A. It's not the internal.
It's not related to 2A.
Okay, well then.
And Eduardo's theory assumes those things are randomly distributed. So you have some.
So then of course you wouldn't get any Q dependence. Okay.
Right. Now we haven't proven that they're not ordered. This is not a high resolution measurement. We just did this in the lab. So if we go back with high resolution, there are materials where like titanium diselenide in the superconducting state, that thing actually becomes incommensurate because there are periodic domain walls that form. And it's very similar. So very similar. This stuff happens in the dichalcogenides. It's known. So what we need to do is go and measure that thing at high resolution and see if the peak is split or shifted. And that would tell you that the domain walls were ordered. And then it really would be some PDW or FFLO kind of phase. So I can't tell you that doesn't happen, and it's known to happen in other things.
Gotcha. And now as for my question related to the earlier discussion of whether or not the 0.28 incommensurate phase, right, what you call CDW1,
Yeah,
whether
this
or
guy.
not, no, sorry, let me take it back. The tetragonal one, the incommensurate CDW,
Yeah,
the one in the orange, correct? So the question of whether or not it's truly a statement of having two kind of domain walls and then what you see is an aggregate summary, or was it something dynamic as you implied that it may be fluctuating? Would you be able to distinguish between the two by applying that uniaxial pressure setup that you discussed?
yeah, and we did.
What do you think would be the difference for these two scenarios if you apply uniaxial pressure?
The older I get, the more I measure first and think second. And so I've deliberately not spent too much time assuming what it's going to do, and we're just measuring it. So here's what happens. So the red, this is this intense. If you measure the intensity of these two different satellites with different orientation as a function of temperature, they have identical temperature dependence. But if you put the system under uniaxial strain, they become different. So the X Fourier component of the density and the Y Fourier component of the density in the incommensurate phase respond extremely differently to strain. One gets stronger and the other one gets weaker. This could be explained in a domain picture or in a or you could say I have a fourfold symmetric CDW that's on the brink of becoming something unidirectional. And then when I apply some strain, it responds greatly. So it doesn't prove which one it is, but there may be with a model and some careful analysis of this data, we may be able to figure that out.
Mm-hmm.
But it seems this effect is not monotonic, like it only.
Can I maybe ask a question because it looks like you don't see me? Peter, this is a kind of layer system. So in tetragonal phase, the charge density wave is essentially in plane.
Yeah.
This 1/3 in trigonal setting, this Q vector, is it in plane still or it's actually three-dimensional?
I can't see you, but you sound like Daniel Komsky to me.
Yeah, well, you're supposed to see me. At least I see me. I see myself.
It's good to see you, sir. What? I'm sorry. Can you ask it again?
I see myself. Well, the question is the following: that in tetragonal phase, CDW is essentially in plane, like in diclinic.
Exactly.
In these trigonal triclinic phase, sorry, not trigonal, triclinic phase, this 1/3 wave vector, is it still in plane geographically, so to say, or
No.
it's connecting different planes?
It's 20 degrees canted with respect to the plane, so it's at an angle.
So it's connecting, it's more three-dimensional essentially.
Everything is three-dimensional. It's a completely 3D charge density wave.
Mm-hmm. So isn't it possible that that's exactly why it's really different? Because if I understand from the first talk, in triclinic phase, distance between layers becomes much shorter, smaller. So the system becomes essentially more three-dimensional. Is it possible that it's something
I don't think so. That the size of the change is very tiny. The structure displacement is very small. I don't know about the dimensionality. I mean, JP may have some anisotropic transport data that I haven't seen, but you know, when the unit cell that you pick changes hugely, but the atoms don't move much, right? So the angles change a very tiny amount. I forget how much when you go from tetragonal triclinic. So you just pick a different cell when you describe the diffraction because you have to, right?
But at least that's significant physical difference between these two different CDW. One of them is essentially in plane, and the other one is actually tilted. So it's not really 2D phenomena.
Yeah. So in other words, there's a very, very small structural distortion, some hundredths of an angstrom or something. And then when that forms, the CDW rotates 20 degrees.
That's essentially, I actually wanted in the beginning to ask a question which you ask yourself, what is the hen and egg problem? Whether this triclinic is driven by the different CDW or it's simply modified. So is there any way experimentally to somehow just to try to influence them, either hydrostatic pressure or magnetic field or whatever, anything to try to to modify and to see whether they will go together or not?
Yes. Okay, let me tell you this. When you apply uniaxial strain, it's sort of the few times 10 to the -4 level. The CDW responds a lot, but the crystal structure doesn't care. You cannot move the triclinic transition with uniaxial strain. It doesn't move, but the CDW changes a lot. So I don't know if that answers the question, but
well, at least it's some hint.
It's a hint. Yeah. To be honest, you shouldn't be asking me that. I probably should be asking you. So.
Okay, very good. Thanks.
I see JP, you have your hand up. You want to ask a question or?
Yeah, thanks. More of a comment just about the domain wall elementary superconductivity. It's just, I'm just pondering because it's, if you think about, okay, there's some competing phases, charge order and superconductivity. And so you might consider that superconductivity lives where the charge order doesn't, so you get an enhanced TC, at least, some partial volume with elementary. And that TC seems to be the same as just to the right of the quantum phase transition. So, naively, they should be the same kind of superconductivity. But there's, the question is, what about the nematicity? So if I think about the right side where there's no triclinic or charge order or anything, and the statement about the TC enhancement due to some nematic fluctuation, is that the same enhancement that's happening just to the left along these domain walls, or is it something different? Right. So this is just, I don't know what to think about it.
I think that's the key question. Yeah. Why, if this TC enhancement is due to some fluctuations, why do those fluctuations live on both sides of this phase boundary?
Exactly.
When one side is ordered and the other one is not.
Right.
So
especially because there's a sort of first order transition between them. So that's very strange.
Yeah. So whatever is
the first orderness doesn't look that strong. That would be one possibility.
Correct.
Yeah. Well, there's definitely fluctuations here, so it's got some second orderness going on.
Certainly, the bulk superconducting transition has a very abrupt jump. Okay, that's my call.
Yeah.
Does the TC respond to strain in that overdose region?
That's a question for JP.
I don't think we have not explored it, no. We're actually doing pressure experiments now to try to pass through this transition region. But we've been held up by some practical issues in doing the experiment, but we're doing it right now, actually. So we can see. I mean,
if one ignores the notion that it's BCS electron, or maybe electron phonon driven is fine. If the fluctuation is in the charge density sector, phonons are by symmetry mixed in. So maybe the whole notion still is that you have a dome and the pairing symmetry is not that much important. So long as the first order, it's not that really gigantic first order phase transition, you still have significant amount of quantum some fluctuations, which I guess Peter can see, and that would presumably be adequate to cause a dome.
So the statement would be that there's charge fluctuations all across here.
Yeah.
And the pneumatic response is secondary to that in some sense.
Well, pneumatic is part of the story.
So
we have
to look for charge fluctuations around 80%.
It seems naively.
Yeah. So I think probably the phonons do something really strange here at the Q vector of the CDW.
Yeah,
but one could identify which phonons by symmetry allowed to couple to these kind of charge density fluctuations.
Yes. Yeah, that, by the way, that's a problem. Yes, I think I already mentioned that. If the incommensurate phase is really C4, it's hard to explain why it's coupling to the pneumatic order, right? Because then they have different symmetry.
No, but the C4, could it be just mixture? It's like a 2Q. The underlying, there's still a Q which, like in FETE, which is pointed along some diagonal direction, but at the end of the day, the order or what you see ends up with a 2Q that's mixed up, or several Qs. I guess you have a more complex Q landscape.
Yeah, I think you have to sit down and, because delta, the rho is modulated at Q. So I think you have to sit down and write down a Landau theory and see what you can make invariant. I wanted to say one thing for the neutron scatterers, if Peng Cheng is still here.
Oh, I'm here, yeah.
People looked hard for antiferromagnetism in this stuff.
No, we looked as well. Like I said, one of the students, we never published anything. Yeah.
Did you look only around pi?
No, we did a powder measurement. This is like more than 10 years ago when this was first done. This was first done by the Los Alamos group, right?
Yeah, that's right.
Yeah. So we quickly looked at it. We're actually using their sample. I mean, we've seen nothing. So we just kept silent. Yeah. After that.
I mean, it would be worth doing. I think the charge gives you some hint of a better place to look. I mean, of course, a powder looks everywhere simultaneously, but if you want to do a more targeted experiment, if the charge and the spin are coupled, then the wave vector of the spin should be halved out of the charge.
Yeah.
Which means you should look here. Right?
Yeah, there should be some phonon softening. I mean, if you form a Bragg peak, then there's some phonons should soften at the position where you see Bragg peak. So now we have single crystals. So it might be interesting to do some single crystal inelastic measurement.
Yeah, and I would go look here and see if there's a magnetic reflection in a crystal.
It's pretty dead as far as magnetism is concerned.
Yeah, you don't think it's there?
No. I mean, I would have published it if I.
I mean, it has nickel, right?
Yeah, but nickel can be non-magnetic.
It can. But there's a question: is it non-magnetic because it's D8 nickel and it's spin 1 and the spins are disordered, or is it non-magnetic because it's not spin 1 and something else?
Yeah,
right. So those are very different things.
Maybe the best thing to do is to look, to get Tomo Yomura, look at with MIOSR. MIOSR is much more sensitive than.
Yeah, that's actually a really good idea.
Yeah, I doubt that there's anything there. I mean, yeah, magnetism wise, yeah, but certainly phonon are very interesting.
Or could NMR be interesting?
Yeah,
I suppose so. I don't understand NMR, but
no, but should it pick up anywhere in the Q space?
Yeah, it's Q integrated. So maybe you see something in the spin relaxation. I mean, we already know the magnetic susceptibility knows about the CDW forming, right?
Yeah, so NMR is actually the sort of very natural experiment to do.
Yeah.
I think NMR was done, but I have to look. It's been a long time.
Yeah, NMR and MIOSR will be interesting. I mean, yeah. But that basically rules out any magnetism, yeah.
So I think Amir's been patiently raising his hand. Do you want to ask a question?
Yeah. So very nice talk, Peter. I have a question regarding going back to your to the phase boundary where you have this tetragonal to the orthorhombic phase transition. So you said in the beginning that not everything where you have this super reflection is a charge density wave. I agree with that. But crystallographically, if you want to describe the lattice and the symmetry with all the Wyckoff positions, taking into account the reflections, obviously for the refinement, you don't take into account this incommensurate reflections. Exactly. So now, so that is crystallographically. So if we now say that this is crystallographically belonging to a tetragonal phase, I have a problem with that because, first of all, it is incommensurate. And actually, I would have expected if it would be the 1/3 reflection, I could do something in defining a different cell. But in this case, how could you actually define a cell when you have an incommensurate wave vector? So already, if you say it's incommensurate in a tetragonal phase, I would say that's a charge density wave, unless you come up with something else.
I mean, it's a fair point. If it's truly incommensurate, the unit cell is infinite, and then crystallography doesn't even make any sense. And if you really want to get into crystallography, there's a super space group formalism that was developed in the 90s by Sander van Smalen and others, where they generalized the concept of a space group to things with incommensurate phases, and they actually refined the structure of tantalum disulfide doing that. It's kind of a brilliant set of papers from the late 90s. You would have to, if you want to do it right, you would have to index this using that framework, which is sort of beyond space groups.
Exactly.
I mean, as an experimentalist, what I do is I just say, well, I'm going to call it tetragonal anyway, and then just show that the peaks sit in strange locations that don't index.
Yeah.
Yeah, but you're
okay.
Totally right.
Okay.
Any other? I see there was Daniel Komsky made a comment in the chat. I don't know if we want to
chat. How do I get to that?
I can read it to you.
Here it is. No, I got
okay.
Your pink plane in triclinic cells tilted by 20 degrees with respect to the great tetragonal one. Yes. But the CW wave vector could still be in plane parallel to intersection of these planes. Where is it in reality? It is in the tilted plane. So this pink plane, well, I called it red, but okay, it's pink. Salmon is tilted 20 degrees with respect to the crystal, the bonds, the planes, and the CDWs lie in this plane. So they're tilted with respect to the crystal lattice, but they're not tilted with respect to the reciprocal lattice.
No, I understand, but it's still tilted with respect to just basic tetragonal crystal axis.
Yes.
With respect to nickel-nickel distances, direction, sorry, and so on, yeah?
Yes,
okay.
Exactly.
So it's really 3D.
It's really 3D.
Okay, good, very good.
Any other questions?
Great questions.
This has been really interesting. Peter, sorry, just before, so how big is the triclinic domains? Do you have any way of?
I don't know. Okay. Too big for us to see on our lab source.
I see.
I think whoever it was said somebody should do E-beam diffraction in a TEM. That would be the way to do it.
Okay. And when you add strain, do you see a response in the domain population?
The triclinic domains?
Yeah.
No, nothing.
Okay.
Triclinic cell doesn't care about strain at all. Only the incommensurate CDW. And the commensurate CDWs also don't care.
I see. Okay, thank you. There's any other questions? This has been, thank you both JP and Peter very much for this really interesting.
Yeah, thank you guys.
Yes, that was
my pleasure.